So this was about the Hale-Bopp comet. And another comet, which is, there are different types of comets. So Halley's comet will be visible in 2061. That's true. So asteroids and meteoroids, basically, sometimes they can enter the Earth atmosphere. When small meteoroids enter, like from asteroid belt, some of the asteroid meteoroids can enter the Earth atmosphere. But if it is a small meteoroid, it burns up in the Earth atmosphere. So, but if it is a large meteoroid, then it will create, like it will have an impact on Earth, or it will create a crater as well on the Earth surface. Any question till now?
No, sir, clear.
Your comets will have different color depending on which gas is present and what is the temperature. So they may have different colors. That's right. Like stars as well, the comets have different colors. Then about the speeds, the orbit of the planets. So sun, as you can see, sun is the center of the solar system. And by far most, it's a massive object. Like compared to any other, sun is a massive object in our solar system. And what force is keeping these planets towards moving around the sun? Which force? What we call that force?
So force.
Centripetal force. And this centripetal force is due to the gravitational pull of the earth, pull of the sun. So we can say this centripetal force equal to gravitational force. So as a gravitational attraction depends on the mass, as sun is having greater mass, so it will have a strong gravity compared to any other stellar object around it. Now, about the orbits, so when we talk about the orbit of these planets, for calculation point of view, what we consider their orbits are perfect sphere. Like example, say this is our sun. Say this is our sun. And if I say draw an orbit of the earth around the sun, so what you usually draw, you will draw a circle. And this is our earth. This is for calculation point of view. Whenever we are calculating, so this is our earth. The earth is moving around the sun. If the question is at what speed the earth is moving around the sun, or what is the orbital speed? What is the orbital speed of the planet, or what is the orbital speed of the earth around the sun? So the formula to calculate speed is equals to distance divided by time, because it. Now, what about the distance? As we consider the orbit is a perfect circle, so the distance traveled in a circle is equals to circumference. And the circumference, the formula for the circumference is 2 pi r. And what will be the r? R is the radius of the circular path. So r is the radius of the circular path. So what is the distance traveled by the earth when it complete one revolution? that's equal to circumference, and circumference is equals to 2 pi r, where r is the distance between the sun and the earth, which is also known as 1 astronomical unit, and divided by time, which is t. So say if I want to calculate the speed at which the earth is moving around the sun, this orbital distance, the distance between this orbital distance, that will be the radius, like radius of this path. And the orbital, this distance is about 150 into 10 raised to power 6 kilometer. So that is the distance between the sun and the earth. And how much time it is taking to completely move around the sun, that it's taking 1 year. So for 1 year, we convert the 1 year into seconds. So 1 year, what we have 365 days. That these 365 days, we have to convert into hours. So we multiply by 24. The hours we have to convert into minutes. So we multiply by 60. The minutes we have to convert into seconds. So we multiply by 60. So this is the total number of the seconds in 1 year. So in 1 year, we have this many seconds, which is about 53600. So these many seconds are there in 1 year. Now, if you need the orbital speed, we have the formula that speed is equals to distance divided by time. And distance, whenever object move in a circular path, the one complete rotation, the distance travel be equal to circumference. So it will be 2 multiplied by pi. The pi is 3.14, and r is the radius. R is the radius, which is about 150 into 10 to the power 6. We are not converting into meter, otherwise the value will be too large. Divided by total time the earth take to orbit in seconds. So this is the total time the earth take to orbit the sun, like in 1 year. So when we divide these two numbers, it will be about approximate
So,
value.
Mr. 298.8.
It's 2 into 3.14 into 150 exponent 6. Yeah, r would be same, like r is the radius between, so we consider it is same. It will be, it won't, by practically it is different, but the average radius we take, that will always be same. So it is about 29.8 kilometer per second. Here 3 zeros are there. By mistake, I put 2 zeros. 3 zeros are there. So it will be 29.8 kilometer per second. So this is like about Earth cover about 30 kilometers distance in 1 second when it is moving around the sun. Like this distance is about 30 kilometer in every second. So using this formula, you can find the orbital speed for any other planet as well. On like some values, you don't have to memorize these values. You just have to use the values and convert the units, like converting year into seconds, and don't convert the kilometer into meter, otherwise the value will be too large. So different planets are moving at a different speed. So this is for calculation point of view, we consider that the orbit of the planet is exactly circular. But in practical, the orbits are not exactly circular. The orbits are slightly curved, or we say elliptical. Like this is a sun. So this is our sun. When we draw the orbit for calculation point of view, we consider it's a perfect sphere or perfect circle. But in practical, what happened? It's slightly bent, or we say eccentric, or this is called ellipse. So the orbit of the planets in practical is ellipse, not a circle. But what is the reason? This will be a common question, why the orbit of the planet is ellipse, not a circle. You should be able to answer this question in terms of energy conservation, like energy is conserved. How we can explain that the orbit is exactly like ellipse, not a circle. So this is our sun, and this is a position of the earth. This is a position of our earth, and earth is moving. Because there is a vacuum, there's no air resistance. So the energy, the total energy of the earth will be conserved, means will be same at all the point. And what is the energy the earth will have with reference to the sun? Because the sun is pulling, there's a gravitational force. So due to the change in the height, due to the position, the earth will have potential energy. So due to the height, the distance from the sun, so due to the height, the distance from the sun, it has potential energy, but it's also moving. So which form of energy the moving objects have?
Kinetic energy.
Kinetic. So due to the height, it has gravitational potential, and due to the motion, it will have kinetic energy. As we mentioned, there is no air resistance, there is no force oppose the motion. So the total energy will be conserved. Means the total energy of the earth will be the total energy of the earth will be equals to potential energy plus kinetic energy. Potential I'm writing PE, kinetic I'm writing KE. So total energy is always conserved for all these planets, as they're not losing any energy to the surrounding. Now, as a result, what will happen? If I say that at this position, the earth is having potential energy, example 50 joules, and kinetic energy also 50 joules. So it has both energies. It is having potential energy and it is having kinetic energy. Both energies are 50 joules. So the total energy is equals to 100 joule. Like the sum will be equals to 100. Now, as the earth is moving, now it get closer. As you can see, like this distance. As you can see, distance from position A was greater as compared to distance from position B. So this is a distance from position A. This is a distance from position B. So distance from position A is greater from the center as compared to distance from position B. So which position it will have more potential energy, at A or at B?
At B.
Potential energy. Because the height is greater, so it will have a greater potential energy at A. At B, it will have a lower potential energy because the potential energy depends on the height, the distance. So means the potential energy decreases. So if the potential energy decrease, like first it was 50, maybe it is 20 now at this point. So if the potential energy is 20, how much is the kinetic energy? If the potential energy is 20, what should be the kinetic energy at this point? The total energy should be 100 as it is conserved.
So it will be 80 joules.
It will be 80 joules. So it means if the kinetic energy increases, it means the earth will move faster. So as a result, what will happen? The earth start to move faster. So when the earth move faster, it move away from the sun. As it is moving faster, it moves away from the sun. So now it is at position C. At position C, now the distance increases. The distance between the sun and the earth increases. So if the distance increase, what happened to potential energy? The potential energy will increase because the distance increase, the potential energy will be more. So maybe here the potential energy is 80 joules. So what happened to kinetic energy? The kinetic energy will be 20. It means the earth slow down. So as a result, the earth slow down. What will happen? The direction of the earth easily changes. So when the direction of the earth, because it's here, why the direction does not change too much? Because it was moving faster. It is closer, but moving faster. So it move away easily. But here, as it move away, the potential energy increases. So the speed or the kinetic energy of the earth decreases. So as kinetic energy decreases, the earth will slow down. When it slow down, it changes the direction more. So there will be a greater change in direction. So as a result, what will happen? It will come closer to the sun again. When it comes closer to the sun again, the kinetic energy increases and the potential energy decreases. If the kinetic energy increases, so it will move further away. So with this reference, what will happen? The total energy is conserved. So as the total energy is conserved, some points it will move faster, some points it will move slower. So as a result, it creates an elliptical. So when we draw the path, of the earth, it will not be perfect sphere, it will be ellipse. Like at this point, which form of potential energy and kinetic energy? Potential energy, which will be greater at this point?
Kinetic energy.
So kinetic energy will be more because it is closer. So potential is less, kinetic is more. So means near, when the earth is closer, it will move faster. But at this point, what will happen? Which energy is more? Potential or kinetic?
Potential energy.
The potential energy is more, kinetic energy is less. So the earth will move slower at this point and it easily changes the direction. So as a result, when it is moving slower, easily change the direction. Again, when it reaches this point, again, the potential energy decreases, the kinetic energy increase. So it will again move faster. When it reaches another point, the potential energy increases, kinetic energy decrease. Again, it changes the direction as it is moving slower. That's how the path of the earth is elliptical, or path of the planet is elliptical. So the idea is that the orbit of the planets are not completely circular, and the shape of this slightly squashed, and what we call this, we call that as ellipse. The path is the ellipse, and the orbit are described as elliptical orbits are there. An amount of orbit squashed, like how much bend is there in the orbit, like say this is a circle, but if I squash the circle, how much I squash the circle, how much I bend the circle, what we call that as eccentricity. It says the eccentricity means bending in the circular path, or squashed in the circular path. So for planets, they are less eccentric than a comet. Like if we want to draw a path of a comet, how we draw? So it will be more, this will be the path of a comet, like more squashed, more eccentric than a planet. And it's the comet, center of the comet should not be the sun. One side there is sun, other side, like one side it is closer compared to other side. Yeah, the planets, the curvature is, that's true. The planets, they have different eccentricity. So their curvature is more as they are moving away. So a planet which is orbiting the space, it's not experiencing the planets which are uh, moving around the sun, they are experiencing the gravitational pull of the sun, and they're moving, so they have kinetic and potential energy, but they don't lose their energy due to the gravitation, due to air resistance, as there is no air resistance. So if a question is why the path of the planets is not perfect sphere or eccentric, so the kinetic and potential energy is conserved. So when the planets get near to the sun, the potential energy decrease, kinetic energy increase, they move faster. And as the planet get away from the sun, the potential energy increase and the kinetic decrease. So they move slower and changes the orbit. So this is the table about the average orbital distance. You don't have to memorize this table. It's just an information. The gravitational field strength of different planets, the surface temperature, the number of the moons, and the density. And you can see there is no correlation with the density and the orbital time. Like density, the first four planets, which are like rocky planets, the remaining are the gas giants are there. They have low density as compared to the rocky planets. But there's no direct correlation between the density and the orbital time. Some are taking more time, some are taking less time. The orbital duration, Mercury is having a short orbit, that's why it's taking about it's taking about 0.2 Earth years compared to